I'm Victoria Jordan. I'm the Vice President of Quality and Patient Safety for Emory Healthcare in Atlanta, and I'm the President-elect for IISE. And it's my pleasure to get us started on day 2, depending on how many committees you're on, right? But on this Monday morning. So now I'd like to introduce today's keynote speaker, Judy Jin. Dr. Jin is a professor of the Department of Industrial and Operations Engineering and the Director of Manufacturing Program at the University of Michigan. Her research focuses on the interface of data science and quality engineering to analyze and integrate system design and operational data for quality improvement decisions. She's been engaged on more than $20 million of grants funded by the federal government and agencies and various industrial companies. Her research results have been widely implemented in industrial production systems and recognized with numerous awards, including 16 Best Paper Awards, Forging Achievement Awards, the NSF CAREER Award, and the Presidential PECASE Award, among many others. Judy currently serves as editor of the IISE Transactions on Data Science, Quality, and Reliability. She's the president of IISE Quality Control and Reliability Engineering Division and a former vice president of Informs. Judy is a fellow of IISE, ASME, and Informs, and we welcome her to the stage today. Dr. Jin, thank you for being here.
Thank you. Yeah. So first, I would like to thank Victoria for the nice introduction and also conference organizer for inviting me to give this talk. It's a truly honor to have this opportunity to give this talk, especially in celebrating 75 years in this IISE professional societies. Okay. So first, I would like to say in today's rapidly evolving industrial and system engineering, we find ourselves at the intersections between many transformative technologies and also data-rich environment. This presents us with many tremendous opportunities and also research challenges. As a researcher, I have been working in the data analytics field in the quality engineering for more than 25 years. My research has been focused on leveraging all those wealth of the data source to develop advanced data analytics methods to enhance the system's quality. So therefore today, I'd like to use this opportunity to dive into the change that we have witnessed over the years in the quality engineering, especially in the realm of the data analytics in quality science. So in my talk today, I will first beginning with motivation, why we need holistic quality. Then introduce the concept of data fusion for holistic quality. Afterwards, I will use some of my project examples to show what is methodologies and applications of data fusion in quality science. So first, let's see the motivations. Why quality matter? We all understand, I think I have some record here. Is that good? Now? Yeah, okay. So manufacturing competitiveness is closely influenced by those 3 essentials. Faster speed, that's in terms of throughput, and also faster response to the customer demands change. And good quality to meet a customer requirement, and also affordable price for customer to buy. And among these 3, it's important to know that quality is the most critical. Without quality, faster speed and the cheaper price, no meaning at all. In another aspect, we all understand product records, due to the quality loss, will significantly affect companies' business operation. Here, I just want to show 3 examples here. The first example is an airbag made by the Takata company in Mexico. So the defective airbag will cause the exploding when deployed during the car crash. The defects are caused by incorrectly using their manufacturing process, installing the chemical compound materials. And when exploding, it's very dangerous because they threw out the sharp metal to the occupants and also drivers. That's a lot of injury caused by this defective airbag. And due to this product record, it cost the company more than 24 billion, and eventually leading the company's bankruptcy. So the second example is the Boeing, the 737 MAX. They have a design flaws and leading to their stabilizing the system. In the maneuver, they could not respond correctly when the sensor sent the wrong signals there. It also has the lack of the training in their pilot. The pilot could not switch the autopilot to the manual operation. So that is to handle that maneuver's mistake. So this is leading to the 2 air crash tragedies, resulting the loss of more than 300 people's lives. It's really terrible, and also impose huge cost on the Boeing. The third example is about the Samsung's Gallery, the Note 7. That has a battery exploding and also catches a fire. That's not only cause the product records cost, but also significantly affect the company's reputation and reduce their market share significantly. So all those 3 examples, we can see that the product quality affected by various factors. That is due to design, manufacturing, or the usage as well. So that is provide essential needs for us to have a holistic quality control throughout the product life cycle. So what is the meaning of holistic quality? Here, it refers to the product overall quality, including the quality itself and also service and experience. So when we try to include this holistic quality control, we should consider all the aspects related to the product design, manufacturing, and also delivery, and the field usage, as well as recycling. So that is a product life cycles control. So we all understand at a design stage, it's very important to provide essential product in verification and validation to avoid the design flaw. As I mentioned before, like a Boeing, the aircraft, the new design, they have a design flaw there. Okay. Second, in the manufacturing, we should ensure the process in control to make sure all the products can meet customer and quality specifications. Third, in the delivery, it's also important to have a good logistic and supply chain operation to make sure the product can be delivered to the customer on time with good quality. And in the in-field operations, we should provide essential the support and the service to prevent the product failure during the customer usage. And also, last one, when we have a product very expensive and also sustainable in the environment concern, we should also consider second life of the product for example, like battery in the electrical vehicles. Okay. So all of the here, we can see to ensure the product quality, the collaborative decisions to consider all the aspects, very important. Now, over my research career, I started from manufacturing process control, and then expanded to the design optimization using computer simulations, and also expanded to in-field usage to provide a customized service. So that's later, my talk will focus on these 3 stages. We also know the holistic quality control. This kind of the research is heavily motivated from the opportunities and the need along with industrial technology development. So next, I would like to show what are the opportunities on the Industrial 4.0 for holistic quality control. So the first, the groundbreaking enabling technology, we all know that is Internet of the Things. That enables us to have a fast the data sharing among all the stakeholders in the global business operation. So that enables us to do the collaborative decision to integrate design, manufacturing, and in-field operation all together. The Industry 4.0 also provides many other transformative technologies, such as fast performance computing, enable us to do high fidelity, the simulations, to do optimal design and also design verifications. And also 3D printing allows us to do fast prototyping and flexibility to do design validations. And the digitizations in the manufacturing allows us to have accurate and also efficient the knowledge representation and the transferring throughout the product lifecycle. Now, moreover, the robotics, automations, and the smart sensors used in the manufacturing process enable us to get real-time process operation data and use that to do in situ quality control to prevent defects. And the most important now is big data analytics using machine learning and artificial intelligence. This empowers our decision makers to discover insightful knowledge from massive data to make a data-driven optimal decision that can avoid subjective bias. So all those here, that is dive into why we need a data fusion research. So what do I exactly mean, data fusion? So this definition I used actually 23 years ago when I gave a job interview talk, tried to describe my research scope and also my research philosophies. Okay. So at that time, the information technology and the data mining are the buzzwords. So that is the hard research area, how we can use the data mining methods to discover knowledge from the data. But now I still feel this definition still remains relevant to our current hard research area in the data-driven decision-making. It provides a comprehensive the strategies to cover the 4 important aspects in data-driven decision-making. So it emphasizes we should collect knowledge and data from disparate sources, and also use interdisciplinary research and approaches to make a system levels optimal decision. So today, we all hear many buzzwords now. big data, data science, machine learning, artificial intelligence, and data analytics. Here, I just want to show my personal view, how those buzzwords related to this data fusion, the framework. Okay, so big data provide more data resources that enable us to do machine learning or more complex artificial intelligence model training, which never be able to do in the past. Okay. And also the machine learning, data science, artificial intelligence, those will enhance our methods to do the better system level optimizations. Data analytics emphasize how to integrate different methods to make optimal decision for specific applications. So of course, as I just mentioned, under the new landscape of the technologies, data fusion now expanded to do the big data, complex system modeling, and also with the rapid data sharing, we can do real-time decision making. And with this AI and the machine learning technology, that can help us to do automatic optimal decision making, to simplify our human or to avoid our humans' bias in the decision making. So here is a busy slide, okay, but generally I would like to show is what is a platform for implement this data fusion for holistic quality in terms of the 4 layers, what I just presented in the 4 key aspects for the data fusion research. So the first layer emphasizes integration to do all this system level thinking, including design, manufacturing, and also in-field operation for holistic quality. Second layer to show what are the data and the knowledge you can collect from each stage. Third layer is showing what a specific decision at each stage, which you also needed to collaboratively thinking to see how they can achieve your first system level objective in holistic quality control. Last layer is really I like to emphasize here is interdisciplinary approach to develop effective methods here. So that is the first, we need to have computer simulations. So that the simulation provide effective interface with the physical system that not only can pre-verify or validate your physical design system, but also can help to incorporate the physical system real-time data for the decision improvement. So that is a digital twin technology now. Second is to have advanced data analytics techniques, including advanced statistics, machine learning, artificial intelligence. Those can be used for discover insights and knowledge from massive data. And we further use a system optimization and control to make an optimal decision. And again, most importantly, we should have a collaborative, integrative thinking to achieve system levels optimization. Okay. So to do this, we have 3 key aspects in the research challenging. So first, in the data analytics, those methods should be able to handle the complexity of the data, especially today's data have the temporal and spatial correlations. Okay. Second, in the decision making, we should consider multiple competitive objectives and also to consider interdependency among the system as well. Third one, it's also important to do risk assessment especially when we consider the stochastic dynamic effects in the operation conditions and also heterogeneous populations for the people to use your products. So to solve those research challenges, here are 3 essentials in my research I like to emphasize. First is computer simulations. That can provide the quick verification and the validation, and also serve as an interface as a digital twin to collect real-time data. Second, we should develop advanced data analytics techniques which can analyze those massive data to make an integrated, collaborative decision-making. Third one is also very important to leverage the in-field operation data. Then we need to have a continuous learning capabilities. So to effectively using those in-field operation data to improve your computer model and also your decision-making. So next, I'm going to use some of my research projects to illustrate those 3 essentials. First is a computer simulation. How do we use that for design optimization? So this application is a try to do optimal design for the vehicle restraint system. First, I like to show is, so the vehicle restraint system design is sensitive to the body size. So this simulation show you is how the different body size will interact with airbag and seatbelt differently. So left side, think left side there, is the regular BMI, the subjects, and the right side is a big BMI people. So you can see they have the different injury risk during the car crash. So how can we optimally design this restraint system? So the traditional design is try to minimize the injury risk for average occupants. Now, of course, it will overlook the injury risk for overly the all vulnerable people, okay? So in other words, you can do conservative design for only the vulnerable occupants. Then this will put the risk on the average people because excessive protection, like the airbag deployment force, will also hurt average subjects' risk as well. Okay. So this motivated us to do adaptive restraint system design. So the idea here for adaptive design is for each specific subjects, we will based on their subject size to give appropriate design parameter such as a deployment force and the characteristic of their restraint system. But this is not easy to achieve for the whole populations. So what we proposed here is a functional design policy for personalized design. So we cannot do individual people optimal design because you have so large populations, different body size, right? So we use a functional design policy to have this function D in terms of occupant's body size. And we optimize this design on this function beta rather than on this D value directly, design value directly. So this strategy helps us to reduce design space significantly. Also, this design function can provide engineering insight. How this body size will sensitive to the injury risk. So this is the motivation we propose the new philosophy, use a functional design policy to achieve the personalized design. To do this, we apply the Bayesian optimization approach. That's we understand we cannot do population's injury risk by using this high-fidelity computational simulation model. So we only conduct 100 subjects using the maximum projected lab scale design there. Then we, based on those 100 people, develop the Gaussian process model. Then using Gaussian process model to predict whole population's injury risk. Then to further consider this uncertainty due to this Gaussian process modeling, we put the upper bound, that is, I'm not here, they do not allow me to use pointed here. I don't know what here, okay, you can show here, okay. So, use this upper risk bound to consider uncertainty of this Gaussian process modeling. And meanwhile, this is iterative, this the optimization procedure. At each the gradient searching, we will add new subjects. Then those new subjects will help to reduce this uncertainty as well. So this is a general Bayesian optimization approach, how to do optimal design. So what are the new research issues we needed to address in this functional design policy? So here, the first things we need to do is to consider engineering design constraint in your objective function. So we need to design the penalty function to appropriately reflect design constraint. Second, the different from regular optimization, Bayesian optimization, in adding the new samples, they needed to add in both the subjects and also the design variables. But now, through our functional design, we simplify this part. We only need to add the new subjects because our design variable will automatically be determined by the subjects. So this can simplify our optimization procedure. However, it also brings out the new requirements in our method. We are not only need to consider the objective functions convergency, we also need to consider the estimated parameters convergency, beta as well. So this is the idea, how we use the existing machine learning methods, also consider specific requirement to extend this method in the particular application. Then when people using the computer simulations, another challenge is we need to make sure computer simulation model can well represent your true systems. So we also conduct the research, how do we use physical tests to calibrate computer simulation model? So the left side showing is a physical experimental test by user test dummy. The right side is our computer simulations. So here, I would like to show those curves, sorry. Those curves shows a comparison between computer simulation results and also our physical test results. So computer simulation results are showing on the blue color, and the physical test is showing on the red solid curves there. So you can see if we directly use a blue color, that is much lower than real test, you will get a weaker design. So the challenge here for this computation model calibration is how to do functional data calibration. This is not easy because the curve as this is functional is very complex. So the traditional way how the people build up a surrogated model, then to combine with uncertainty quantification cannot be directly applied here. So we propose an integrative approach to combine functional fitting, uncertainty quantification, and also design optimization together as an integrative approach to solve this problem. So here I finish about the first essential. Second, I like to talk about doing the manufacturing. We like to use in situ process sensing signal to prevent the defects. That's going beyond just a traditional quality control doing the quality inspection. This slide shows the basic principle, how we emphasize process-oriented in situ process quality control. That is, here we understand product quality, showing here, will sensitively affected by your equipment and operation parameters. And those process operation performance can be monitored by the in situ process sensor signal. We all understand on the Internet of the Things and also the many advanced sensor technology, so we can quickly collect real-time the process operation data. Then how we can use those data to improve or enhance the process in transparencies, so we can monitor those in-process sensor signal reflected by process response. Then meanwhile, through the process model here, we can use those signals to predict what the quality will be, even before you can do the quality inspection. Then this gives us the opportunity to do the control to prevent the defects. So this gives us a general idea how we emphasize process-oriented in situ quality control. To do this, the first task, very important, to do process model. By including those in situ process sensor signal. Why we need to include those process sensor signal? So you can understand the intuition behind of that. If you have a multiple production line, you have same machines setting on the same parameters. Are they going to produce the same quality of the product? May not. Because frequently, you have many unknown process disturbance there. E are showing here, okay? So that's why in order to fully reflect your product quality, you may like to find some in situ process sensing signal, which can reflect those unknown effects. So we have two models here. One is I call the process signature model. How this process variable or equipment setting parameter with unknown factors affect those process signature signals. That is the S model. Second is quality prediction model. So I already mentioned we should not only include the process or equipment operation parameter, we also should include process sensing signal S there. So in this way, you can fully predict the quality based on this process model. Here, I also summarize what are the common research issues in using those process sensing signal. So the first is data dimension reduction. We know process sensing signal will be very high dimension, okay? And it's important to extract the small dimension of the features for process monitoring and diagnosis and control. We can use different methods, such as different data transforms or regularization on the variable selection. Second, for monitoring those signals pattern change, we can do early warning about the process behavior. Then this part, our traditional SPC methods, statistical process control method, I often used. Third one, we like to identify the patterns change of those in situ process signal. That can enhance us to do fault diagnosis. Third one, we can even control the process signals change than to do the defects prevention. That's the traditional statistical quality control robust design, and also more advanced SPC, supervised APC control can help us to do defects prevention. I would like to see when we analyze those signature signals, we needed to have advanced data analytics method to develop those models. And those models involving closely related to what type of the sensor data we have. So I showing these slides just give a rough idea how the field has been evolved over the times based on the data availability. Okay. So axis shows the arrival time years, how those methods be developed. Yeah, yellow is just show what type of the model. Then blue shows what type of data characteristics. Then y-axis depends on what types of the sensor data available. Okay. So at the earlier stage, 1920, we all know in the quality control Shuha control charts. Okay. So that is only focused on RID data. Then when manufacturing process become mass production, we are able to collect continuous product measurements. Then data become autocorrelated. So various time series data developed to consider autocorrelation over the measurements. Then when we have a complex sensing data, which shows a different sensing profile change, we can use multivariate functional data fitting and multi-scale decomposition, and also even today, deep neural network, to consider those complex profile shape change. We further have multiple sensor signals to combine together. How we consider the cross correlations between sensors, and also to separate within sensor signals. So that's become temporal or spatial correlations. Then tensor data structure is raised or developed. Today, I just saw the award ceremony before our data quality reliability sections. The awarding the people is using tensor data. Okay, I'm really glad we got that attention as well. And within the image and video signal be increasingly used in the process monitoring, then the tensor data also help us to capture the spatial among the picture, the image pixels, and also the temporal and the spatial correlations between different frames in the video signals. And recently, in the laser sensor has been popularly used, and the 3D point cloud data with unstructured the complexity in the data, that we vox-based the type of the data also be interested in the field as well. So next, I'm going to use specific examples to talk about the multi-channel waveform signals, why we like to use a tensor data structure. Okay. So here shows the example in the forging operation. Okay. We have the full sensor signal collected on the forging press. Then the one important thing for their maintenance is how this machine moving down, what kind of the patterns will indicate the health of this press machine, press the status. Okay. So when the machine is moving down, the ideal situation they should smooth. But because it's unbalanced vibrations, that sometimes they will have a front and back, or left and right, those unbalanced patterns. Those patterns can be used to guide maintenance actions. How can we automatically identify the knowledge about this machine's health, how they are doing to guide the maintenance? So that is the idea. We needed to find cross correlations among those four sensor signals. So before I give the solutions, you can look at those four sensor signals here. So what's your guessing about cross correlation among those four sensor signals? So you may, when I ask those to the engineers in the press, so virtually they give me answer is sensor 1 and sensor 2, I correlated. Sensor 3 and sensor 4, I correlated. So this will reflect left and right unbalance. Is this correct? If I enlarge this signal to you, so you can see from these two sensor signals here, those have the dynamic similar pattern. So the correlation should reflect the close dynamic pattern rather than the mean value of the signals. So this really reflects what is the vibration pattern here. Okay. So this indicates to identify cross-correlation is very important. How we can do it mathematically. So first we need to know how to represent the data. So traditionally, people use this stack-up model structure that they put the sensors just stack up together, 4 sensor signal as one row of the signal in the matrix. That is a problem. They will confounding the between signal correlations. They could not identify what is a cross correlation among the signal. So that's why we propose using this, tensor data structure. So we should have those one additional mode to separate this between sensor correlations. Now we use this tensor data structure. We did the UMPCE. That's give us the consistent results of what we see from the signals. So that is your sensor signal actually is 2 and 3 are highly correlated, and 1 and 4 are highly correlated. So this gives us automatic discovering of the cross correlation by using this tensor data structure for multiple sensors. So the second example is how do we use the signature signals pattern to indicate the quality check problems. Okay. So here is the application is about ultrasonic welding that's used to install the battery for the electrical vehicles. Okay. So we understand it's infeasible to use those direct measurement on the welds to check the quality because of many welds in the process. Okay. So this motivated us to use the in-process signatures to predict the product's quality. So here, the in-process sensing signal, including here as these 4 types of the important signals, the power and also the force and LVDT, and also microphone. So how can we use those multiple sensor signals to indicate whether these welds will be defective or not? So that is the motivation here. So we use the classification methods. And because of the limited training sample, we use the LDA linear classifier. And also considering how those models be trained, we use a tensor structure to cover the multi-channel signals. And the new research issues here is how do we consider the defects? Because those small number of the samples, when we estimate within cluster covariance metrics, we got unstable results. So we added this penalty to ensure our classifier parameter training will be stable. Third one, how we do in situ the process control to prevent the defects. So we understand under normal good condition, the signature signal will be repeatable, like the power, first one I'm showing here. And the second one, when you have better quality, then the signature signal pattern will be changed. If we can detect this pattern changing earlier, like here, then we can do the process adjustment. For example, we can adjust the clamping force then to ensure they have enough power, because at the earlier stage, the power signal is lower than normal. So we can prevent the later defective welds. So this is the idea how we can use in situ signatures feedback to do in situ quality control. But the challenge here is what time you should do control. So we should use SPC supervising what time is good to make an effective control action. So this tool is critical. If it is too earlier, that is your monitoring performance may not be good because you may not find the change significantly. If it is too late, that you do not have control opportunities to compensate this change. So we develop a SPC, supervised adaptive control here. So due to time limit, I'm not going to show the detail here. So next example is how do we use the cross-learning between the different products to enhance the quality prediction. That is the 3D printing process. We understand that the inlet defects in the 3D printing will be very critical. However, to inspect those defects will be very expensive by using CT scan. So that is motivate us. Can we use in situ process signal to predict what is the likelihood the produced 3D printing will have excessive inlet defects or not? So here we use the optical spectral signal. That is, you can see here. So this signal is very dense in terms of both wavelengths have autocorrelation and also the deposition process in the spatial correlation as well. So in this high dimension data, we needed to do data dimension reduction. Here we use a deep neural network to do feature extraction. So we train the encoder and the decoder together to make sure our feature extraction is reliable here. So we use the different neural network, CNN, convolutionary neural network, and also LSTM, long short-term memory neural network, to represent the spatial correlations. The second challenging here is we do not have many parts in the one same setting. So that is due to the nature of 3D printing. So how can we learn those different parts together for better training of the model? Then the third part is we know we only have a limited label data, but we do not want to also lose the information from the unlabeled data. So how can we train the model better? By using semi-supervised learning strategy. So here is just a framework. Okay. So we use a clustering method to do the quality prediction. That is clustering, spectral clustering were used because that can represent the defects, the shape, spatial correlation structure. And also, here, the H stands for clustering the model parameters. So how we can learn this parameter through the multiple different products. So the idea here is we add L2 long on these model parameters. The third part, how we construct semi-supervised learning, that is we consider the labeled data and the unlabeled data spatial correlations. Okay, so now I'm talking about for the manufacturing in situ quality control. Next, I'd like to say, how can we integrate the manufacturing acceleration test and also in-field operation data together to improve the reliability validation to ensure the customer can receive their required reliability. So here we need to consider the products may be used on the heterogeneous operation conditions. So we all understand accelerated life test is popularly used in the product design and the manufacturing stage to verify the reliability requirements. To plan this accelerated life test, the acceleration factor is the most critical parameter in the design, this ALT test. How do we accurately get this parameter? Here, we all understand we're using this AF is a standard for acceleration factor. They are all factored by, their parameter here is N and EA. This is sensitive to the material and the product characteristic failure modes. Okay, so if people working on reliability, you know. But those two parameters normally is based on their literature or their prior product experience to give the both experience-based parameters. And those parameters may not exactly fit what is the real actual number in the field operations, in their specific products at different field operation conditions. So how we get these parameters accurately? Then we can combine the in-field operation data. We use those in-field operation data, the manufacturing based on the warranty data, collaboratively learning different environmental conditions by the customer. They can estimate what is the failure rate based on the field data. Now, in the accelerated life test, we can also predict what will be in the field operation, the failure rate. Now, these two differences can be used to calibrate our AF, these important factors. So this is showing the idea how we combine the both accelerated life test and also in field operation to calibrate those unknown parameters in the engineering model. The next part at a certain essential stage here, that's in-field service. I like to see how to predict in-field performance for different customized the service. That's we can consider the heterogeneous operating condition for connected system. So the application here is connected vehicles, how it can provide cost-effective warranty service for different customers. So we all understand the vehicle's health condition is heavily depends on what is the drivers use those vehicles. And also depends on what is their traffic, road condition, and weather conditions. For example, for the AC, air conditioning, okay, so we can monitor the vehicles, compressors, the pressure signals to indicate how their AC health status. However, those AC pressure signals sensitive to the environmental using conditions, like driving behavior is speed and also environmental temperature. And in the combustion conditions, we can also consider, you can use the torque force to reflect how efficient of the combustion performance. But this torque force also related to how the people driving behavior, acceleration, deceleration, of those things. So we consider the usage condition as a covariates, how they affect these in-vehicle performance sensor signals. Because here I'm showing just some example on the curve, you can see how complex of those signals tests. So we needed to develop the advanced machine learning methods for prediction of those vehicles sensor signal. So this prediction can be used for anomaly detection, and the results can help us to do customized service, and also maybe used later for insurance as well, and also can help to do better fleet management. So for anomaly detection, so the general idea here is you have a normal operation vehicles, so we can build up the baseline for this prediction, what will be under those covariates condition. So the one challenging here is how we can find out what is the normal vehicles to build up this prediction model. Then during the real-time operation stage, we can use this normal model to predict what is supposed to be in those vehicles on the real condition. Then we compare the difference or deviation between the predicted the system sensor signal with the real measurements. If these two not match together, that indicate your performance change. Okay, so that is the idea how we use this prediction model to do anomaly detection. There are three challenges here. We do not have the labeled data to tell the people which vehicles on the road we are on the normal condition because the earlier degraded vehicles, they may not be able to separate from the normal vehicle. Okay. Second challenge is you have a heterogeneous, complex, those sensor signals for those reflect those environmental or operating conditions, how we can handle those complex data. Third one, for new vehicles, you may not have enough data to train the model. So how we can train the new vehicles model? Here, I provide those general strategies framework. So first, we needed to have advanced the sensor fusion model, which can handle the complex covariance variable. Second, we needed to have a multitask learning to overcome, we do not have this labeled data. So the idea here is we use multitask learning to group, to automatically clustering among the road vehicles, what they have similar behavior. That will trigger us to do a similar service for those group of the vehicles. Third one, for new vehicles, we will find within their limited data then which cluster they will close to have the similar behavior. Then we borrow those close to similar cluster to train this new model. And finally, in order to protect the customer privacy, we may not need to share all those data together. We only need to share their model, which is built up on their edge computing in their specific vehicles. So this is a general framework idea how we solve the problems. Okay. So due to time limit, I'm not going to talk about details of the mathematics. Here, I also like to show we have many learning methodologies emerging in the machine learning and the deep neural networks. So those learning techniques will enhance our data analytics methodologies in the quality science as well. So for example, like encoding and decoding training I just mentioned before. So for data dimension reduction, active learning can help us to select efficient samples for labeling. And also the game model can help us to generate more simulation data for modeling. And the transformers, that is a very fantastic adaptive learning strategy, can help enhance, find the relevant, important samples in the modeling. And reinforcement learning to combine both exploration and the exploitations to optimize this decision within limited budget. And zero-shot learning can help us to detect unknown defects. So I would like to say the data fusion with all those learning techniques will enrich the methodologies in the quality science. And also holistic quality control with emphasis on the personalized X. X stands for design, manufacturing, and also in field usages. Okay. Can help us to enhance customer satisfactions to generate broad impacts for the quality science. So finally, I like to conclude my talk. The data fusion for holistic quality has great opportunities as well as challenges to advance the quality science under this data-rich environment. It requires multidisciplinary efforts to using all those integrated approach to make the holistic optimal decision. Finally, but not least, we needed to have a close collaborations between academia and also industry to implement those technologies, data fusion methodologies, for the broader impact in the quality engineering. And also, I'd like to use this opportunity to thank all my project sponsors and my former students and also current students who contributed significantly in today's my talk. And also, I have many research collaborators and other students which involved on my data fusion research who made the tremendous help, support. And I would also like to thank for them, although I don't have time to talk all of the projects. So finally, thanks to everyone here, the audience, to come to listen to my talk.